Hello, my name is Aidan Tremethick. This is my Year 5 STEAMS Constructions Inquiry, specifically on the topic of space. My unit will be titled STEAMS, a STEAMS Constructionist Inquiry. This unit will explore how students can learn through an interdisciplinary approach that connects science, technology, engineering, arts, mathematics, and social sciences. This focus is on a hands-on inquiry project where students design and construct a sustainable Mars habitat. Throughout the presentation, I'll unpack the rationale, the curriculum connections, and how constructionist learning theory shapes the pedagogy, and finally, how the unit can be assessed, evaluated in alignment with graduate teacher standards. Ultimately, this presentation demonstrates how a STEAMS approach transforms a traditional science topic into an immersive, creative, and socially meaningful learning experience. So why STEAMS in Year 5? It's a very good question. A STEAMS framework deliberately blurs the boundaries between subjects. For Year 5 students who are naturally curious, collaborative, and imaginative, it offers the ideal environment for integrated, inquiry-based learning. We promote this holistic development by drawing together the analytical rigor of STEM with the expressive and interpretive power of the arts and social sciences. Research shows that integration increases motivation, transfer of knowledge, and creativity, because students recognize that learning finally through an inquiry-based constructivist method has meaning beyond just the classroom. In this unit, students will explore how technology, environment, and society intersect when humans extend life beyond Earth. They investigate scientific facts about planets and ethical questions such as how do we share resources fairly and who owns space. This multi-dimensional view of learning meets the needs of diverse learners and prepares students for a world that values problem solvers and collaborators, as opposed to just being boring, old, rote memorizers that doesn't engage young learners. So first of all, we must establish what is constructionist inquiry. So constructionist inquiry is grounded in Seymour Papert's theory that learners construct new knowledge most effectively when they're making a public artifact, something that can be shared, tested, and discussed. Unlike traditional instruction, where the teacher delivers information, constructionism places students at the center. They ask authentic questions, design experiments, build their own prototypes, and reflect on their own outcomes. Learning becomes a cycle of creation, reflection, and iteration. In this project, students design and build a model Mars habitat. They continually refine it as they discover new information, mirroring how scientists work in the real world. This pedagogy also encourages metacognition. Students will think about how they learn, not just memorize what they know. It aligns perfectly with Vygotsky's social constructivism, emphasizing collaboration, dialogue, and peer scaffolding. Essentially, the classroom becomes a mini research lab where mistakes are viewed as opportunities and success is measured by growth, creativity, and understanding. So what happens when we combine the STEAMS and inquiry model? Visually, imagine a diagram with constructionist inquiry at the center, surrounded by 6 interlocking circles representing all the STEAMS disciplines. Each discipline contributes something unique. For science, it supplies content knowledge and investigation skills. For technology, it provides digital tools for modeling communication. Engineering encourages design thinking and practical problem solving. Arts fosters imagination, empathy, and aesthetic expression. Mathematics ensures precision, measurement, and data interpretation. And social sciences bring ethical, cultural, and environmental context. These elements rotate around the inquiry circle of ask, explore, create, test, reflect, and share. The arts thread through each phase, allowing creativity to drive understanding. This model ensures learning is authentic, collaborative, and iterative, not just a boring checklist of separate tasks that have no connection to one another. So when we look at the curriculum links, we'll look at science and mathematics, and this unit is firmly grounded in Australian Curriculum version 9. In science, it will address Earth and Space Sciences, ASCSSU078. Students will understand that Earth is a part of a system of planets orbiting a star, our sun. They'll also engage with science as a human endeavour, ACSHE081-083, by exploring how scientific discoveries influence society. Mathematics links include measurement and geometry, ACMMG113, where students use scale and coordinates to construct their accurate models. And statistics and probability, ACMS P119, where they can collect and analyze data, such as planetary distances or resource requirements. Through this, mathematics becomes a tool for exploration, rather than just this boring, isolated, out-of-touch subject. Students will apply numeracy in authentic contexts by mapping, graphing, and calculating, reinforcing a conceptual understanding and relevance to what they're putting their minds to. When we look at the curriculum links of technology, arts, and HASS, the technology strand of ACT-DEK019 and ACT-DEP024-2028 ask students to design and evaluate solutions for sustainable futures. Here they consider how a space habitat could recycle air, water, and waste, mirroring environmental concerns right here on Earth. In the arts, outcomes such as ACA VAM 115 and ACA MAM 064 encourage students to plan, produce, and present artworks and media pieces. They might create digital posters, logos, stop motion films, documenting their mission. Within HASS, content descriptors like ACH ASSK120 examine resource use and sustainability. Students can debate what is essential for human survival and reflect on their own ethical stewardship. By weaving these areas together, this unit allows students to view space exploration as a scientific pursuit and a human story with design, ethics, and creativity. So when we look at the integrated project, the Space Habitat Challenge, now that we've got our framework and what we're dealing with, our pedagogical focus, let's look at this. So the anchor of this unit, this construction inquiry unit, is the Space Habitat Challenge. Students are placed in the year 2030, far into the future, and briefed by Mission Control to design a self-sustaining base for six astronauts. Teams of 4 or 5 take on professional roles. An engineer designs the structure, a scientist researches environmental conditions, a mathematician handles measurements, a designer artist manages aesthetics, and a communicator prepares the final presentation. The challenge requires research, sketching, prototyping, testing, and presenting to an authentic audience. The format mirrors real-world STEM careers while also empowering students with agency. The scenario also supports differentiated learning, an important thing to factor. Visual learners can build models, analytical learners can crunch data, and creative learners can design artwork or narratives. Collaboration truly fosters peer mentoring, leadership, and social growth. So when we look at the learning activities we have, each discipline will contribute to the whole. Science and engineering, students test insulation methods, materials, and investigate how plants might grow with limited water or light. When we look at technology, using tablets, they code simple simulations of rover movement or design their base digitally. Mathematics, they complete scale ratios, habitat volume, and daily resource consumption, applying real formulas meaningfully. Arts, students design mission patches, paint planetary landscapes, and compose creative stories or soundscapes from an astronaut's perspective. Social studies, they can discuss governance, how would laws or leadership work on Mars, and compare it with systems on Earth. These activities cater to multiple intelligences and learning styles, promoting engagement, equity, and inclusion. They also strengthen the general capabilities of critical and creative thinking, ICT capability, and personal and social capability. When we look at formative assessment strategies, they will drive the learning in this unit. Students will keep a science and design journal where they record their hypotheses, sketches, data tables, and reflections. This journal provides insight into their thinking and growth over time. We schedule regular checkpoints. For example, when the team completes a habitat blueprint, they present it to their peers for constructive feedback. I observe group collaboration using it as the educator, using a checklist noting participation, communication, and problem solving. Short exit tickets and quizzes capture individuals' understanding of key concepts like planetary order or measurement conversions. Finally, self and peer assessment rubrics allow reflection on teamwork and contribution. These strategies ensure students continuously evaluate and improve their own learning, embodying the iterative nature of constructionist inquiry. Now let's jump to summative phase, which will culminate in 2 parts. First, the group will present its Mars habitat model at a school-wide expo. Assessment uses an integrated rubric measuring 5 domains: scientific accuracy, design and engineering process, mathematical application, creativity, and teamwork. Second, each student will write a reflective report, almost like an astronaut log, where they describe their role, justify their design choices, and evaluate what they learned. This ensures individual accountability and written communication practice. Moderation with a colleague will help achieve consistency and fairness, and parents and peers are invited, strengthening homeschool partnerships. The result is a celebration of learning that values process as much as product and meets standards 5.1 to 5.3 regarding assessment and feedback. When we talk about the alignment with graduate teacher standards, this unit demonstrates a clear alignment with these. 1.1 to 1.2, it reflects an understanding of Year 5 physical, social, and intellectual development and employs strategies aligned with how students learn through activity, curiosity, and collaboration. 3.1, challenging yet achievable goals are set through open-ended tasks. 4.1, mixed ability grouping and role assignment ensure inclusive participation. 7.3, families are engaged through newsletters and the Space Expo invitation, encouraging shared pride, a continuum of learning from the home to the classroom. And in 7.4, there will be consultation with local experts, perhaps a planetarium educator or university outreach coordinator. This will extend professional engagement. Through these links, these graduate standard links, the unit models reflective, ethical, and community-connected teaching practice. So to conclude, this Space Habitat Challenge exemplifies how STEAM's learning and partnered with constructivist inquiry make education dynamic, purposeful, and joyful. Students don't simply memorize boring facts. They live the experience of being scientists, engineers, artists, and citizens. They learn that science and creativity aren't mutually exclusive, but they can coexist. Mathematics inform design, and social responsibility extends beyond Earth. This integrated model nurtures curiosity, confidence, and a growth mindset. It demonstrates how thoughtful curriculum design can meet academic standards while igniting imagination. As teachers, we aim to cultivate lifelong learners who ask questions, take risks, and see the world and beyond it as a space for exploration. When students stand behind their Mars habitats, explaining their design with pride, we see authentic learning in action. That is the essence of STEAM's education. Students constructing knowledge, meaning, and hope, one idea at a time. Thanks for listening.